So I'm happy today to give this presentation about incremental stability and incremental input to state stability. So today I will talk about analysis and also design. It will be an overview, a survey of many existing work. So it's not all the results that I will present are by myself or by my co-author, but actually I will give more overview and then provide some new results in the last couple of years. So this is the outline of the presentation. So first of all, I will speak about necessary condition for incremental global asymptotic stability. Of course, after introducing the notion of incremental global asymptotic stability. Then I will give some characterization in terms of Lyapunov or contraction analysis about incremental global asymptotic and exponential stability. I will then characterize the notion of incremental input to state stability, and finally go towards design, in which I will show a few techniques to make a system incrementally stable via feedback. And finally, I will talk about a natural application of incremental stabilization, which is that one of synchronization of nonlinear system. Okay, so first of all, I will just give a slide about the notation that I will use all along this presentation. So given a dynamical system described by an ODE, so we will talk about finite dimensional ODE in this presentation, I will denote like capital X with the arguments x0 ut, the solution of this dynamical system x dot equal f of x and u, that start from initial condition x0 at time 0, subject to this input u that lives in some set calligraphic u. Then standard notation for class K function. So a class K function alpha is a function which is 0 at 0 and strictly increasing. It is K infinity if it does also go to infinity when the arguments go to infinity. And finally, the standard notion of class KL function beta for functions which are class K in the first argument and decreasing to 0 in the second argument. Okay. So given a system, an autonomous system described by an ODE x dot is equal to f of x, we say that this dynamical system is globally incrementally asymptotically stable, and in short, delta gas. If we can find a class KL function beta such that when we pick the difference between two trajectories originating from two different initial conditions x1, x2, this difference is bounded by the class KL function, in which we recognize in the arguments the difference with respect to the initial condition. So basically, this condition means that whatever we initialize the system, any two trajectories of the dynamical system will converge to each other as time goes on. Moreover, we say that the system is also globally incrementally exponentially stable if this class KL function is actually a form of an exponential behavior. So beta of SR is like some exponential function in time. Okay, I will give some properties. I will give some properties about why it is important to study this notion of incrementally stable later on during the presentation. So far, I would like to point out that that there is a difference between globally asymptotically stable and exponential stability, and I would like to make a comparison with respect to standard notion of stability, asymptotic stability and exponential stability, to understand a little better if there is actually any difference in this notion in the incremental context. In particular, it is good to recall that we may have global asymptotic stability but not global exponential stability, because of two different phenomena. For instance, the first example is x dot is equal to minus x cube, and we see that this system is globally exponentially stable, but not exponentially, is globally asymptotically stable, but not exponentially, because at the origin, the equilibrium is not exponentially stable. And indeed, this can be easily shown by looking at the linearization around the origin of the system. And we see that the linearization actually is zero, so we cannot, with standard Lyapunov arguments for the linearization, we cannot state if it is stable or not, but we can actually construct a global Lyapunov function that will give us global asymptotic stability. On the other hand, we have a second example, which is x dot is equal to minus arctangent of x. And we see that this system is globally asymptotically stable. Again, origin is globally asymptotically stable because from any initial condition, solution will converge to the origin. But it is not globally exponentially stable because at infinity, the speed of convergence is not fast enough. And indeed, the arctangent is saturated. So when we are very far from the origin, so for instance, when arctangent is close to its bound, well, we will have a linear convergence towards the origin. And then when solutions are close to the origin, we will recover exponential stability. So we see that there is a different phenomenon appearing in this characterization of stability. And in the last year, we try to understand better if there is any difference between global asymptotic, well, if we can characterize in the same manner the same behavior in the incremental context. So the first result that I will give in this presentation is about some necessary condition that naturally appears in the incremental setting due to the fact that the class KL function is uniform with respect to the difference between two initial conditions. And in particular, we have this following result, which says the following. So suppose that there exists this class KL function such that our system satisfies this bound. So our system is incrementally global asymptotic stable on the time of existence of these two solutions. Then the following assertions are true. So first of all, incrementally global asymptotic stability implies that the solutions are forward complete and bounded. Second result that we have is that also that incremental global asymptotic stability implies also the existence of a unique equilibrium, and such an equilibrium is globally asymptotically stable. And third result, we have that given any R, it exists a K and a lambda such that the difference between any two solutions is upper bounded by the maximum between R, which is arbitrarily small, for instance, and a term which is exponentially decaying. Okay, so let's analyze and comment these three items one by one. So the first item state that solutions are forward completed boundedness. So this is a nice property that we have, which is inherited from the fact that solutions satisfy this bound. So increment stability, it means that it prevents finite escape time. So if a system in the autonomous case is incrementally stable, while solution needs to be bounded, they cannot have finite escape time, and they are also forward complete. So in general, this is nice because we started from the notion that we asked, from the property of convergence between any two solutions, and we can conclude that actually they need to be forward complete. So in general, it means that when we work with incremental properties, asking for forward completeness is in general not at all restrictive, because it is a necessary condition. Second item, it shows that if an autonomous system is asymptotically, globally, incrementally stable, then necessarily it admits only one equilibrium point, which is globally asymptotically stable. The fact that it's globally asymptotically stable, it's a direct consequence of the fact that the difference between any two trajectories must converge to zero. So the difference with respect to the equilibrium and any trajectory must converge to zero. So the equilibrium must be globally asymptotically stable. I would like just to point out that in the context of incremental global exponentially stable, this result is very well known, and the proof usually relies on the application of Banach fixed point theorem on the solution. Here, however, the proof is slightly different, and so it is somehow a relaxation because we use the fact that just gas, delta gas, it implies the same result. And the proof goes as I sketched here. So since it is delta gas, we can show that one solution at least is bounded. Hence, all solutions are bounded, and therefore, using omega limit set, we can also show existence and uniqueness of an equilibrium. And the third point is also very important because it establishes a fact that in the incremental context, actually, the difference between delta gas and delta gas is very mild, because this bound is telling us that when the solutions are very far from each other, they had to converge also exponentially. So the class KL function has to be an exponential function at infinity. And this means that if your system is delta gas, it will be also delta gas at infinity. And basically, since R can be taken as arbitrarily small, delta gas implies, delta gas implies actually delta gas everywhere but at the equilibrium in some sense. And so again, the takeout message of this study is that if you want to use delta gas for some application, as we will see at the end of this presentation, so if you need incremental properties in some application, asking for incremental exponential stability is not very restrictive, because actually the fact that you are asymptotic and not exponential, it's just a local behavior near some equilibrium. So in general, asking for exponential, it's also good. And as engineering, we know that at the equilibrium, in general, you would like to have, in general, local exponential stability. So asking for Js is not restrictive. And another comment that we can deduced by this property is the fact that since the system has to be delta just at infinity, it implies also that the system has to be global exponential stable at infinity. And thanks to this property, we can actually rule out immediately some system to see whether they are or not incrementally stable. And so, for instance, these two examples show that these two examples cannot be incrementally global asymptotically stable, because their behavior at infinity is not exponential, but is slower than linear, and it is slower than exponential. So this can be also used as a test to certify incremental properties in dynamical system. Okay. So we have seen some properties about the incremental properties, and I would like to highlight that these properties can be deduced by just analyzing solution of the dynamical system. Of course, one can ask himself, how can I characterize and study the incremental stability properties of a system? In literature, there are many different ways and studies, and I'm gonna spend a little of time to make a survey about existing results in literature, about existing characterization, and to see how they are connected to each other. So to cite a few of examples, we see that one way to characterize incremental stability is through the use of incremental Lyapunov function. Another approach that has appeared in literature in the last 10 years is the one denoted as Finsler-Lyapunov function. Then there is also a very popular approach, which is often denoted in literature as contraction approach. And finally, there are also some other approaches which are denoted as logarithmic norms that I will not talk about them very much in this presentation. So the first characterization in terms of Lyapunov stability is the one of incremental Lyapunov function. The main idea to study incremental stability is somehow to double our plant. So since we want to look at the difference between solution, the main idea is to double our dynamical system. So instead of looking just x dot is equal to f of x, we will look at x1 dot is equal to f of x1 and x dot 2 dot is equal to f x2. And we will try to characterize the incremental stability property in terms of stability of the diagonal set x1 equal to x2. And we have this result by David Angeli in 2002, which tells us that a system is incrementally globally asymptotically stable if and only if there exists an incremental Lyapunov function. Now, the incremental Lyapunov function is in general just continuous, and it satisfies the two typical bounds. So first of all, the typical sandwich bound, sandwich inequality. So this Lyapunov function V is upper and lower bounded by the norm of x1 minus x2 with some class K infinity function underline alpha and bar alpha. And the second inequality is given in terms of solutions of V, of a property of V along the solution of the dynamical system x1 and x2. And in particular, we see that the V has to be decreasing along solution in terms of this inequality in which we have appearing this integral of a positive definite function of x1 minus x2. Of course, we immediately recover global exponential stability in the case in which the sandwich bound is in terms of a quadratic bound, so underline alpha and bar alpha are quadratic function, and also in case in which we have exponential decay of our Lyapunov function B. Okay. And one other remark, this theorem, in the paper, it is proved that this characterization is an if and only if. So basically, if your system is incrementally stable, then there exists a Lyapunov function satisfy this bound. And conversely, if you have the incremental Lyapunov function satisfy this bound, then you can automatically ensure that the solution satisfies the incremental bounds. Okay. A second characterization that has been proposed to study incremental stability properties is the one denoted as Finsler-Lyapunov function introduced, for instance, by Fournier and Sepulcre in 2014. The main idea is to construct what we call the lifted or variational system. Sorry for the small typo here. And basically what we will study is the system x dot is equal to f of x and the variational system obtained by small variation around any trajectory of x. So we will call this small variation delta x. So delta x is a small variation around a trajectory of x. And we will study the stability of this delta x dynamics. And we can state that the system x dot is equal to f of x is incrementally globally asymptotically stable if we can find a Finsler-Lyapunov functions, C1 Lyapunov function, and some class K infinity function, such that the following two bounds are satisfied. Again, we recognize the first bound as the classical sandwich bound for the V, and the second inequality, as again, is that in terms of dissipation, so it's a dissipative inequality, so V dot along the solution of x and delta x satisfy this negative inequality. Recall that of course, again, by asking underline alpha and bar alpha to be quadratic and alpha to be linear, we obtain immediately incremental globally exponential stability. Just a couple of remarks. So the first one is that actually this study in the original paper by Fournier and Sepulcre has been generalized to generic manifolds M and constrained delta x to the tangent bundle of M, so not necessarily in Rn. Here in this presentation I'm focusing on Euclidean spaces. And the second remark is that in their original paper, this Finsler-Lyapunov function is just a sufficient condition, but it was not stated whether it was necessary or not. I will come back on this later. Finally, we have another approach characterizing incremental stability properties, which is the one denoted as contraction analysis, which nowadays is, in the last few years, is very popular. The main idea of contraction analysis is to study just the variational system, so delta x, and we have the following result, claiming that a system dot x equal to f of x is incrementally globally exponentially stable if and only if we can find a function p which take, so it's a matrix p that depends on x, which take positive symmetric values, and some other bounds, such that the following two bounds, two inequalities, are satisfied. Again, we recognize somehow a sandwich inequality. Indeed, we ask this matrix P to be uniformly bounded from above and below, similarly to what we ask for the Lyapunov functions. And the second inequality is again somehow, I will come back on this, but a generalization of the Lyapunov inequality, because basically we are taking the derivative of P along the vector field F. Here we have to be a little careful, because since P is a matrix, we have to deal with tensor. So we recognize three elements in this LFP operator. So we have the classical P times the Jacobian of F and its transpose, and then we have also this element, which is also denoted as I wrote in the remark, as the derivative of P along the vector field F, that we can construct we can define it in two different but equivalent ways. Either we take the limit of P evaluated at x plus s of x minus p of x divided by s, taking the limit for s going to 0, or we can take it thinking about having a lot of elements, so all the elements of P are such that this guy, the derivative of P, is the Jacobian of P times the vector field F, so that we can again end up with a matrix dimension n times n. So this result has been stated by Vincent Andrieux, Bayu Jawardana, and Laurent Prali in 2016, and this result is actually characterizing incremental globally exponential stability and not asymptotic stability. So this is true only for global exponential stability. But actually, it is an if and only if the result. So this condition is sufficient in general, but it is also necessary under some smooth assumption on the vector field F. Okay, so the sufficiency part, of course, can be found much early in literature. So for instance, in this work by Lohmiller and Zlotin, or by Simpson, Porco, and Bullo, they were characterizing the same contraction properties in terms of same inequalities. The necessary part is interesting because the construction of P follows similar ideas to how we can build a Lyapunov function, but actually is constructed from the variational system. So basically, instead of taking as in Lyapunov function, in converse Lyapunov theorem, instead of taking the integral of the solution, here we take the integral of the transition matrix corresponding to the variational system. Okay. As I was saying before, this condition, we can think about it as a generalization of a Lyapunov matrix equation, inequality actually. And if we think about x being at particular trajectories, we can see it also as the Lyapunov matrix inequality for time-varying linear system. Moreover, P can be used to define a Riemannian metric, and we can also construct a Lyapunov function thanks to this function P. The way it is done is the following. So we take a length, we can imagine to take any path between any 2 points x1, x2. We take any length connecting these two paths. And actually, we take the minimum, between all the lengths and this C1 path, we take the one that minimize the path, the length associated to this Riemannian structure P. And by minimizing along all such paths, we get a Lyapunov function v of xn1, x2 that satisfy the bounds that we have before. So we actually construct an incremental Lyapunov function. And so, I will now, another point is that in the case in which P is constant, we also recover what is called in literature the so-called Demidovich condition. So in this case, the P dot part, let's say, vanish. So we just obtain P times the Jacobian of F plus its transpose, and this has to satisfy the strict inequality. And in this case, showing that we can construct an incremental Lyapunov function is actually much easier. One way to do it, which is very straightforward, is to construct the error coordinates E as x2 minus x1. And by recalling the fundamental theorem of calculus, it is immediately seen that this quadratic incremental Lyapunov function satisfies V dot is smaller than a norm of the E square by simple computation. Okay. So I will not spend too much time on this, but I would like to understand whether there is some equivalency between the three approaches that I presented so far. And actually, it turns out that in case of incremental exponential stability, these three approaches are completely equivalent from the analysis point of view. Actually, there are also very recent results showing how to construct a Finsler-Lyapunov function from the existence of an incremental Lyapunov function. We can also construct the incremental Lyapunov function from the contraction, which is what I just shown. And we can do also the opposite, basically showing how to construct an incremental Lyapunov function from the Finsler-Lyapunov function, or going from contraction to Finsler-Lyapunov function. And so all this somehow clarifies that all the three main approaches that we can find in literature to characterize incremental properties are completely equivalent, at least in the context of Euclidean space. This is one way to go from one to the other. Of course, they are equivalent from the analysis point of view. We will see maybe from the design point of view, they are not the same. There are also some other alternatives that I will just briefly mention in somehow tools to characterize incremental stability properties of a dynamical system. For instance, there are non-Euclidean contraction methodologies introduced, for instance, recently also by Bullo in 2022 and co-authors, or logarithm norms and metric measure about the Jacobian, introduced, for instance, by Sontag in 2010. They provide, of course, a very useful sufficient condition for analysis, but to the best of my knowledge, these conditions, they are not always necessary, and they can also be difficult to employ for feedback design. So in the rest of the presentation, I will mainly focus on the contraction approach and show how to use it to characterize it for incremental ISS property and also for feedback design. I would like also to give a very nice example that has been suggested to me by a student recently, last CDC actually, which is the following one, which is non-trivial, and actually it is shown. I wanted to show to highlight how Riemannian metrics and Riemannian approaches can be important even in the Euclidean case. In particular, this example is the following. So we have a scalar dynamics, which is x minus x cubed plus 10. And we would like to know whether this system defines is an incrementally stable system or not. Now, clearly, if we study its Jacobian, we immediately see that its Jacobian is given by 1 minus 3x squared. And so when x is very small, the Jacobian is positive, and we may be tempted to say that this system is not a contraction, is not incrementally stable, because around the region, the Jacobian is positive, so we may have problem. And indeed, if you just try to apply the definition that I gave before with an Euclidean metric approach, you will see that you cannot establish contractivity. However, if we pick a Riemannian metric defined as follow, so we take a constant term, so P is a constant term that we have to choose, and then we have minus arctangent. So basically this function is something that when you go to minus infinity is constant, then around the origin it decreases, and then again it is constant. So this function, this P is uniformly bounded by P and P plus 1 by construction, and its derivative is minus 1 over 1 plus x squared. Now, if we compute the LFP term of this Riemannian metric along this vector field, what we actually can show is that we can show that LFP is negative if we select the number p, the real number p, the scalar p in appropriate way. So for instance, for p equal to 3, you can numerically test that this polynomial is always negative, and therefore LFP is always negative. And so, thanks to the use of a Riemannian metric, we can conclude that this system is actually globally, incrementally, exponentially stable. And actually, it was quite surprising to me because it is saying that even if the Jacobian sometimes is positive, it does not exclude the incremental behavior. Okay. So without further ado, I will now go to the similar characterization in terms of incrementally ISS properties. Now we say that a system is incrementally input to stay stable if we can find a class KL function and a gamma function such that the difference between two any true trajectories is upper bounded by the sum of two terms. The first term is again a class KL function which is decreasing in time and depend on the difference of the initial condition. The second term is a term which depends on the difference with respect to the inputs that we apply to this two dynamical system. So basically, we have a system, we take two initial conditions, two different inputs, and we look at the difference between the corresponding trajectories, and we say that the system is globally incrementally ISS if it satisfies this bound for any two initial condition and any two inputs u. Of course, since we are looking at difference between trajectories and inputs, if we take the same inputs, the incremental ISS system needs to be also incrementally globally asymptotically stable. Of course, then if B it's a class KL function, we also have exponential behavior. Okay, so here is just a couple of properties that are very useful about incremental ISS properties, because they can be useful in many practical applications. So I just wanted to quickly recap it. So if we have a system which is incremental ISS, then we know that for any constant u, solution will converge to a unique stable equilibrium point x0. Moreover, if the input is t-periodic, then solution will converge to a unique periodic solution of the same period. And moreover, we know that incremental ISS is preserved via global diffeomorphism. So all these three properties are very nice, and then they've been established by Angeli in his seminal work in 22. Moreover, we also have that a cascade of incremental ISS system is also incremental ISS, and similarly to the non-incremental context, if we have the interconnection of two incremental ISS system, we can conclude that the overall system is incremental ISS if we have an incremental small gain condition verified. So this extends in a natural way what we know about ISS cascade and interconnection of ISS system, but in the incremental context. Of course, similar to the stability case, we can ask ourselves, is there any characterization in terms of Lyapunov, ISS Lyapunov function? And the answer is yes, meaning that a system that dot x equal to f of x and u is incrementally input to stay stable if and only if we can find an incremental ISS Lyapunov function satisfying classical bounds that extend the notion of ISS Lyapunov function in the incremental context when we consider again two systems x1, x2 with two inputs u1 and u2. Just a small remark, the converse is true, so the necessary part, so the existence of the Lyapunov function inherited from the ISS properties is true only whenever U lives in compact set. While the sufficiency part, meaning that if we can find an ISS Lyapunov function then the system is ISS, well, this is global also in the input. Okay, so of course, as before, now we are interested in giving an alternative characterization of incremental ISS in terms of contraction properties. And what we have here is that if you have your system, now I will restrict from now on to the end of the presentation to a more particular class of system, which is the one of input-affine nonlinear system. So instead of having a general vector field f of x and u, I will consider systems which are x dot is equal to f of x plus g of x and u. And so for this class of system, we have a nice characterization in terms of Riemannian contraction approach, which is the following, which is, so if the system, the autonomous part when there is no u, so our vector field f satisfy the incremental global exponential stability contraction inequalities as before, and moreover, we have what we called in literature Killing vector field property, then the system is incrementally input to state stable. Now, it's important to understand a little better what is the effect of this Killing vector field property, meaning that we have that the g, so the input u appears through this function g of x and u, and this vector g has to be a Killing vector for our Riemannian structure P. Okay. So to understand a little better what is the effect of why do we need this Killing vector property, let's consider the variational system. So in this case, when we consider the variational system of x dot is equal to f of x plus g of x and u in the presence of u, because of u of this vector field g of x and u, we will have a new term which is appearing in the variational dynamics. And in particular, we will have that when we consider variation of delta x and delta u, we will have the part in terms of delta x that is, as before, the Jacobian of f, but now we have also the Jacobian of g appearing multiplied by u. And then we will have g of x times the variation of u. Now, as we said before, incremental input to state stability property implies also incremental global asymptotic stability properties. So if we take u1 and u2 equal to the same value, basically when we consider that there is no variation in the input, so delta u is equal to 0, we have a variational system that should be global exponentially stable, uniformly in u. Meaning that if we apply the condition of the Riemannian condition of before to this variational system, we obtain two terms, LFP plus LGPU that has to be negative for any x and u. But of course, if this term is LGP is different from 0 and LGP is negative, well, we may found an input u that destroy our contractivity property. And so if we want to be this inequality to be verified for all x and u uniformly in u, what we need to have is this term LGP is equal to 0, which is this Killing vector property. So this Killing vector property plus contractivity of the open loop system is a sufficient condition to guarantee incremental ISS. One important point is that necessity so far remain to be proven. And in particular, it's not clear whether incremental ISS, it implies the existence of a matrix P which is uniform in U, and that gives us contractility. Some remarks to understand a little bit, even a little better, these properties. For systems that are linear in the input, so x dot is equal to fxu plus bu, the existence of an Euclidean matrix satisfying the Domidovich condition is sufficient to guarantee incremental ISS property. And this because the Killing vector property, since it is a property on differential of G and P, while it is trivially satisfied for constant matrices. Moreover, for scalar dynamic, we can always build a matrix satisfying the Killing vector property by taking P of x equal to G of x minus 2. And so if G of x is uniformly bounded, we can immediately take this as a candidate metric to verify if the system is contractive with respect to the metric or not. We also have a nice result in terms of incremental ISS stability and transfer input to state stability, meaning that if we consider the variational system, quite surprising, we have that if the system is incremental ISS, then the lifted system has to be ISS uniformly with respect to delta U, and with the same convergence rate. And so this is some recent result that we proved in the CDC 23. Okay, so I will move now to the stabilization part of this presentation, and in particular the question is how can we make a system incrementally globally exponentially stable via feedback. And so I will shortly revise three main methods. The first one based on what we call control contraction metric and the use of infinite gain margin. The other two methods are the incremental version, which exists in literature, of the so-called backstepping and forwarding techniques. Okay, and the main idea is that all these three methods are based on a contraction approach, and this is why also I was saying that we have different tools from the analysis point of view, but from the design point of view, they maybe not be equivalent. And the main idea here is that if we set u equal to some function alpha of x and we look for a matrix satisfying this condition, we boil down to condition that depends just on x. While if we try to construct a feedback from a incremental Lyapunov function, for instance, then we will have to deal with difference between two inputs. And it is not clear how design feedback law in this case, as we typically, contrary to what we typically do in classical control Lyapunov function approaches. So we have this result that if you consider again our input-affine system and we have this in this set of conditions verified, then we can state that, oh sorry, there is a small typo in the statement, but basically we can state that the closed loop system is globally incrementally exponentially stable and also input to stay stable with respect to input D appearing at the input. So signal D appearing at the input, so satisfying the so-called matching condition. So the three conditions that we have here that are denoted in literature also as control contraction metrics are the following one. So yes, so the first condition is LFP minus PG G transpose P smaller than minus Q. Now, if we specialize this condition to the linear case, we immediately recover the algebraic Riccati inequality. And so basically in the linear case, it means that if AB is a stabilizable pair, then the algebraic Riccati inequality as a solution for any Q, and therefore we can design a feedback law. This is somehow a natural extension in the contraction framework. Of course, when you are in the case in which the system is linear in the input U, you can look for an Euclidean metric, for a constant matrix P instead of Riemannian metric. In this case, you have this set of simplified conditions, And that can be also give a more powerful design in terms of linear matrix inequality or Euler-Kuchera parametrization. These are very recent results. And for instance, in the case in which the nonlinearity satisfies a monotonic condition, our set of inequalities before can be casted into an LMI. Okay. So these three conditions basically as follow. The first one that we need is the somehow incremental stabilizability condition. Then we need again our Killing vector property, and this is what it allows us also to ensure incremental ISS property. And finally, we need an integrability condition because basically the control feedback phi is Jacobian, must satisfy this equality P of G. Now, this integrability condition and Killing vector condition, of course, may be in general restrictive. They are very restrictive because if we want to find the feedback, so we need to solve the set of inequalities at the same time. So we need to find P and phi satisfying this set of inequality, which is not easy because they are inequality state dependent. So it's an infinite dimensional problem. And recently we tried to work out on relaxing this Killing vector in integrability condition, and we show that actually we can allow approximate condition for numerical approximation based, for instance, of neural networks tool, or again some relaxed analytic condition to have more degree of freedom to solve these inequalities. I will just refer to the work because of time. Finally, I would like to point out two other methodologies to design a feedback that give you incremental stabilization properties in closed loop. So the first one is about backstepping. So the typical approach to do backstepping when you have a cascade of two systems is the following one. You consider x2 as a virtual input for the x1 after you know how to stabilize it. And you make a change of coordinate such that then you just have to stabilize the second dynamics. And such a feedback procedure can be applied recursively, and there exists incremental version in literature that tell you how to design a feedback satisfying how to obtain incremental stabilization in closed loop with the extension of these ideas. Similarly, the forwarding approach is somehow the dual. You have a cascade, but in an opposite way. So for backstepping, we deal with lower triangular form. For forwarding, we deal with upper triangular form. Again, the idea is that you recursively stabilize this cascade form in a two-step approach. First, you stabilize one system, and then you stabilize the other via a change of variable. Again, I will not spend so much time to talk about this because of time, but you can find recent works that dealt with this forwarding approach in the incremental setting and show how to make a system, a cascade system of this form, contractive via feedback. Okay, now I will go to the end of my conclusion by quickly showing an application, a direct application of incremental properties, which is the one of synchronization of nonlinear system. And this is a very natural application. So the typical synchronization problem or consensus problem that one of the best basic idea that we can try to solve is the following one. So you have a set of n agents that communicates between each other. They are described by some dynamical system. In this case, we will consider input-affine dynamics, and you want to find a distributed law such that you achieve synchronization. Basically, all the xi converge to each other asymptotically. And of course, you have a constraint because the input u has to depend only on the local information and the information of the neighbor. So it cannot depend on the full state or on the full graph, on the full information of the network, because this would be like a centralized algorithm, but just on the on the local information that are available at each agent. Okay, for linear system, the nice thing about linear system is that we have fully characterized this problem, this synchronization problem, and if you have stabilizability of the single agent dynamics plus connectivity of the graph, it implies you can synchronize your graph, your network with a distributed law. And in particular, you can find a unique feedback matrix K such that the so-called diffusive coupling solve your synchronization problem. So we call it diffusive coupling because basically the control action UI depends on the state I minus, so the difference between the state I and the state of the agent to which is communicating which. So this calligraphic Ni is the set of neighbors I of the agent I. And so you take the difference between xj and xi, so any two dynamical agents that are communicating, you make the difference between the two states, and this give you, when you sum it, this give you your control action feedback. And this of the global exponential synchronization problem. Now, some remarks which are important is that this feedback gain K is based on the algebraic Riccati inequality, because it gives you what we call an infinite gain margin property, meaning that if we multiply K by some coefficients K, then this is still a good control feedback. And so we have a design step, which is split into steps. So first you solve an algebraic Riccati equation, you take this K, this BP, and you multiply it by a scalar K, which depends only on the connectivity of the graph, and in particular on the smallest non-zero eigenvalue of the Laplacian matrix L. It can be shown that the synchronization problem is actually equivalent to the stabilization of simultaneous stabilization problem for a set of dynamics of this type in which lambda are the eigenvalue of the Laplacian matrix. And this is why the solution is based on this infinite gain margin property, because you need to find just one K which stabilize all the dynamics of this type in which lambda I can vary. Of course, as we have seen before, this algebraic Riccati inequality can be extended in a direct manner to the contraction framework with the control contraction matrix approach that I shown before. And therefore, if you look at the synchronization problem in state feedback for input-affine dynamical system, and you suppose that the graph is connected and the sufficient condition for the control contraction metric approach are satisfied, you can automatically solve a synchronization problem with a similar diffusive coupling, in which you take the phi coming from the control contraction metric approach and you multiply it by a scalar K, which depends only on the connectivity of the graph. Just a couple of remarks before I go to the conclusion. The construction of the Lyapunov function, it depends whether the graph is leader connected or undirected. In one case, what you take is to take the Riemannian energy associated to the distance between the leader of the network and any agents of the graph. In the second case, in which, so this is graphically what is going on. So you have a network with the leader, and what you will take is the green arrow that associates the distance between the Lyapunov function. So you make the Lyapunov function as the sum of the individual Lyapunov function of the energy associated between any agent and the leader. In the case of graph without leader that are undirected, the construction of the Lyapunov function verifying synchronization of your synchronization problem is a little different. And the way it is done is to construct a Lyapunov function as a sum of the energy of the edges. So the edges are the links, basically, and what we do is to consider any two agents communicating between them. You take the Riemannian energy associated to them, you make the sum of all this energy, and this gives you a Lyapunov function ensuring stabilization of the synchronization manifold. we have done some, so here is the last part of the presentation in which I wanted just to show how this condition that may seem very complicated from the analytical point of view, and actually they are, because you need to solve somehow ugly nonlinear PDEs. Nonetheless, they can be approximated on compact set to obtain nice condition. So in this example, we considered some Lorentz oscillators, so chaotic behavior, with an input u that enters with some trigonometric function. And of course, if you want to find an analytic solution for the inequality that I give you before, that give you the feedback that solve the synchronization problem, of course, this is very complicated because you have a PDE in which polynomial and trigonometric function are appearing, and I don't even know whether a solution actually exists or not. However, we look for numerical solution based on deep neural networks approach. What we do is to describe our matrix P by a neural network composed of many parameters, and we try just to approach it numerically as best as possible. In particular, we try a neural network with a cost function that satisfies some bounds, and we see that we have 4 elements to optimize, one corresponding to the Riccati-like inequality, one approximating the Killing vector property, so we cannot solve a numerical problem asking for LGP equal to 0, so we just try to make it LGP as small as possible, and finally imposing positiveness of P for the 4th term. And simulation are quite nice because numerically we could solve the problem, and we see that actually we have simulation, we have synchronization of our Lorentz connected network, and we also put random noise, etc., etc. Okay, so without further ado, I go to the conclusion of this long talk. So just as a summary, what I did is to present an overview of analysis tools for incremental stability, an overview of contraction-based feedback design tools, and we apply these tools to the context of state synchronization of multi-agent system. So, of course, I didn't have the time, but there are many other applications in which contraction and incremental properties pop up naturally and are very important, such as tracking, regulation, and observer design. An open problem that it's really critical and would be very interesting to solve is to have more insights about the necessity of these Killing vector properties for incremental ISS property. And just concluding with some other topic which are related on which I'm working on currently, so which are about characterization of incremental global asymptotic stability properties in the context of time-varying system. Here this presentation was about autonomous system, but of course you can extend all of this notion in the case in which time appear. We are also trying to look at about this incremental stabilization property with some adaptive techniques, and also try to extend this notion to the discrete time context and hybrid, and finally also work with this Riemannian contraction tool in the context of K contractivity, which are some new tools that appear in literature quite recently. Just want to thank my former and current students and all the collaborators for this work, and to show you very quickly, here there is a very non-exhaustive bibliography that I put at the end of the presentation about all the results that I cited in this presentation about stability, input-to-state stability, control contraction metrics, backstepping, forwarding, synchronization, and ongoing work. Thank you very much for the listening.